So, good evening, everyone. Hope you are aware that APSSDC is conducting series of technical and non-technical webinars to improve the skills of faculty, students, and the youth of AP. So, as a part of that, we have started the webinar series on latest trends, and today we have a webinar on GDMT, the key aspects of quality design and manufacturing. And today our resource person is Mr. Ganesha Garu, and he is highly effective trainer with more than 7.5 years of experience in project planning, job assignment, and worksheet maintenance, surface and sheet metal design. He has extensive knowledge of wide variety of CAD applications used and assisted 25 plus projects. He stays constantly current with newly released updates and incorporates them into training materials and handle hands-on technical workshops like two-stroke and four-stroke engine. So welcome to the session, sir.
Thank you, Mas.
Thank you, sir. You may continue with the session, sir.
Okay. Good evening to one and all. Without wasting any time, let's start the session. So, this session topic is GDMT. So that acronym for GDMT, that is Geometric Dimensioning and Tolerancing. So why GDMT is needed and what is the main role of this GDMT in manufacturing and normal industry? So this is the overview of the complete session that what I will going to carry out now. So initially I will going to introduce with the GDMT and how exactly it has got emerged and what are the different types of standards are there, how exactly the GDMT has been used in different types of industry like small scale, medium scale and large scale industries, and what are the different GDMT applications are there in different varieties of engineering fields, either it may be civil engineering, mechanical engineering or electrical engineering or electronics. So GDMT is must for all the interdisciplinary courses as well. And why GDMT is very important and how exactly it plays a very important role in industries and in the manufacturing sector especially. And for this GDMT, we have 14 characteristics and I will going to explain those 14 characteristics and the importance of them in manufacturing of any product. So that I will going to explain it in detail. And then we're going to see LMC, MMC and RF's condition, that is least material condition and maximum material condition, and regardless of features, and how exactly the GDMT will going to have in industry and how exactly you have to understand the GDMT while manufacturing anything. So all these we're going to discuss in further slides one by one. So I will just take the complete layout of an industry. If I consider an industry, as I mentioned in the beginning itself, we have different kinds of industries. Again, we're going to have a small scale industry, medium scale industry, and large scale industries. So among all these types of industry, we have one more, that is OEM, so original equipment manufacturers. Original equipment manufacturer itself will going to have subclass of manufacturers or vendors for getting the accessory parts or subassembly parts. If you are having a car manufacturing firm as a OEM or a bike OEM or any automotive or aerospace OEMs, then definitely for those automotives and all those transportation vehicles will going to have plenty of sub-assemblies, small parts. You can just have a visualization of car, bike, and all the transportation vehicles into your mind. So you can easily say that how many number of parts are available in those the transportation goods or vehicles. So for manufacturing that, a huge components and the number of components required for that is very very a what it's very very larger in the mass, and as well as to get the in detail what manufacturing of that particular drawings and all, then it's a tough job actually. So as I said, the part production and all the things I have made it as a what a line diagram. So we're going to have a continuous contact with all these peoples when you are having a manufacturing of any product. So we will going to have a customers and vendors. As I said, OEM or any large scale industry, medium scale industry, or small scale industry. All these types of industries are interlinked. The large scale industries are giving the orders for medium and medium scale again are giving the order for a small scale industry, so are interlinked. And in the same manner, so each and every firm will going to have all these kinds of sectors. That is, we're going to have a design. If you are having any product, just assume that. So here from the management level, I will just have a overview of the complete company from the small scale, medium towards large scale. So each and every companies will going to have the same scenario and the process and the schematic. So the management will be there, and then we're going to have a design team to produce a concepts and giving for manufacturing and to get output of it. So to design any component, you need a tooling properly. That means if you want to produce any component, any product, so for preparing or creating or fabricating or manufacturing, particularly the tooling is required. That means the jigs and fixtures that what we're going to use to bring that product into reality. Yes.
Ganesh, you're we are unable to see your PPT.
It is.
Can you just share the screen? Yeah.
I have shared actually. It is on mode.
It's not visible. Can you please revisit again?
Is it visible now?
No.
Wait a second. Is it visible?
Yes. Perfect. Thank you.
Fine. Thank you. So as I was talking about the different types of industries, so all the different types of industries come under same roof, a single roof that is from management, design, and then tooling, and then we're going to have a production with the help of the tooling, design, and the product design that what we have made. After production, we're going to have an inspection to get a quality output, and then we're going to send it to the assembly section. After getting that assembly, then we're going to have the service, and then what purchase sales. So all these things we're going to have. Along with that, we're going to have pricing, planning, routing, everything. So in terms of product development and product design and manufacturing, so we simply call this as a concurrent engineering. That means each and every interdisciplinary fields are interlinked with one another, and each and every information has to go from one end to another end. So continuously the flow of information that will carry from the management to the level of customers, and each and every information will be secured. So why I'm telling all these things is GDMT is not a complex subject or not a complex thing to understand. It is as simple as the language that what we are having now, as we are having a language what exactly I'm speaking now is an English. So in the similar manner, we're going to have a different languages to have a better communication. So in the same manner, in each and every industry, we're going to have the language of drawing. That is what we're going to cope up with the GDMT. So GDMT will going to give, and which enhances the understanding of each and every manufacturing of product. Because if you have any product, if you have a concept of that particular product, then you need to have a drawing of that particular product. If you are having a drawing, then you can't what simply take that drawing and do something on it, but you need to have a proper tooling design and the equipment, and a little skilled labor must be needed to understand that particular drawing or engineering drawing and then execute it and bring a new product. So while bringing, what are all the difficulties that normally the industries are facing is, so and also why this GD&T all come into picture and why it has been arrived. So each and every functionality and everything that we're going to discuss. So GDMT means geometric dimensioning and tolerancing. As I said, the name itself is saying so many things: geometric dimensioning and tolerancing. As the geometry says, geometry either it may be a circle or rectangle or it may be a triangle. So if I take a circle, it is a geometry. If I take a square, that is a geometry. A rectangle is also a geometry. Ellipse is a geometry. So all these geometries are having a particular specification to define circle as a circle, square as a square, rectangle as a rectangle. We have defined it and we have given some rule to define and to judge as that particular polygon or a particular feature. So circle has a diameter. Either we can define with the help of diameter or radius. Square we're going to define with the help of length and breadth. Rectangle as well as similar to square, length and breadth, but with the variation of length. And ellipse, we're going to have major axis and minor axis. So the profile or the geometry will going to have the dimension. So that is geometric dimensioning. Then we have a tolerancing. So why that tolerancing is needed? Because we have a geometry, we're going to have a dimension. Why can't we have just a geometric dimension? Why do we need this tolerancing? So that always have the question in your mind. So that tolerancing is very much needed, because as we know that we human beings are not a perfect perfect in all the aspects. We'll always have a error while doing manufacturing. Suppose if you want to manufacture any shaft or any blade or any plate of particular dimension. Suppose you take an example of a shaft of diameter 25. If you want to manufacture it, you will not going to manufacture or fabricate it with the exact size of 25 mm. A small deviation will be there. Obviously, either it may be a 25.1 or it may be 24.9 or it may be 24.99. So likewise, we will going to have the variation in the dimension of the design or drawing that what we have made. So that is why to have what the tolerance limit, so that we can accept the particular product that what we will going to manufacture. If I have 25 mm diameter output, that's what that intended design that we have made for shaft. Suppose if you have machined it, then if you got 25.1 and 24.9, whether do you need to accept that particular shaft or not, that is important. So if you reject that particular component, then obviously what will happen, you will not going to have the particular functionality where exactly that shaft will be used. That is very, very important again. So in the similar manner, that means to say, if you have one product, what is the functionality of the particular product and where exactly it has been used, whether it is a single entity which is not useful for any assembly, or whether that particular shaft is used for fitting any other components, or whether it is needed to be fitted with the hole. So likewise, we have plenty of option for any single product that we're going to launch or that we're going to have a manufacturing. So then obviously that tolerance zone has to be there. Why? Because as we have 100% max, out of 100% max, 35% is a minimum marks to pass, and 85 plus is a distinction. That means to say the quality of the marks, that how exactly we're going to differentiate. In the same manner here also in manufacturing sector, we're going to define the different tolerance zones. So that within that tolerance zone, if it comes, then obviously that product will be accepted. We're not going to reject that component. Otherwise, the investment that what you will going to make for design, tooling, everything will be lost if you have a bad product. So that is why in each and every industry, as I said, from the small scale towards the large scale, so the precision work is very, very important, as we are being a human with machines. We'll always have a little error, micro or even a nano level errors will gonna happen. But depends on again the application and the quality of output that we require. So here we have GDNT. It has been increased in past 15 years since from that ISO 9000. It was got an emergence and it was got an advancement. Now GDNT practices are specified in ANSI Y14.5M 1994, and it was revised in 2019. And we're going to have a continuous revision of this ASME as well. So, as I said, GDNT is a language. It is a drawing language actually for all the manufacturing sector or all the engineering fields. So we're going to have GDNT as a drawing language, so that we're going to have a product output with the help of design drawing and tooling drawing. So for that, we must have a standard, as we have the English, US English, UK English, and we have our native languages. So all the languages are having their alphabets. In the similar manner, here also in GDNT, we have, so GDNT is an alphabet in a standards of ASME. So we have different types of applications and different types of standards we're going to use in industries. That is ASME, ASTME for materials, and ASTME. So ASME, American Society for Mechanical Engineering, and ASTM, American Society for Testing and Materials. So these standards are being used in all the industries nowadays. And we have ASME standards which has been expanded. So in all this, we are under ASME 14.5. That is completely related to dimensioning and tolerancing. As I mentioned, geometric dimensioning and tolerancing will come under ASME 14.5. We have set of chapters in ASME standards under that. So dimensioning and tolerancing will come under 14.5. Orthographic and pictorial views, line convention, letterings, all these metric drawing sheets, size formats, everything. That means in manufacturing sector, we're going to use the drawing sheets, everything. So each and every aspect that what we're going to carry out in industry, that has been standardized and that has been secularized with the rules, so that each and every person can understand. So it is just a globalization or universalization of the language of a drawing, so that we can have better manufacturing. Even now we can have an example of transportation itself. So we have the manufacturing of locomotives now by Alstom. So it is a outside company, and that means it is a foreign company which is making manufacturing of Indian locomotives. So likewise, to understand and to have a communication, we have to globalize, and we have to have a universal language to understand each and every aspects. So why I have shown these types of lines? Because in engineering drawing, so this is very, very important. GDNT, we're going to have dimension and tolerancing, but to understand the drawing, we must understand what all the different types of lines are there. Among all these different types of lines, only two types of lines plays a very, very important role. One is solid line and another one is dash line or invisible line we normally call. That means if you are having any visuality of any product, whatever the product that you will going to see, suppose just take an example of a rectangle itself with or a cuboid. It would be better if I take an example of cuboid. If I see cuboid from any other one side, it will be appearing just like a rectangle. Sorry, not a rectangle, it's a cube. So it will be just like a square. So front view will be a square, top view will be a square, and side view will be a square. So while visualizing, you will going to have a solid line. Suppose if you are not having any visualization behind, suppose if you are having a step or slot in that particular component, then obviously we're going to use hidden lines. So I will just take an example of this table. So the table, what you are seeing in the screen, that is 27 point plus or minus 1. So this table may have a deviation over a surface. It may have 26 or it may have 27, or it may have 28. That means to say, here you have a tolerance zone or geometric tolerance zone you can call, because we have a zone for or giving upper limit and lower limit. So tolerance is nothing but we have two limits. Within that, we're going to have a zone. So in between that, if you are having a variation of the table surface, obviously, if you have manufactured or fabricated, then variation of the profile, if that comes within this upper limit and lower limit or tolerance zone or geometric tolerance, so then obviously we're going to have the acceptance of this particular product. That means suppose if this table has been manufactured and the surface is coming with respect to the variation of this curvy profile, and which is having a 26 dimension or a 27 dimension or 28, either of three if you are having, then definitely we're going to accept that component, and then we will going to sell that component. So likewise, so you must require whether you need to accept this particular product or not, because suppose if you are not having this dimension within the limit that what you have specified, then obviously we're going to have a rejection of that particular component. So in this case, it's okay. Just for the sake of example, I have taken how exactly we're going to have the tolerance zone. And next, we'll move on to why this GDMT is very, very important in industry. And as I said, it is a language which is very much needed to have a better communication with the design person and the production person. So, and also the entire team that what you have seen in the beginning itself, the entire industry layer that what you have seen, each and every person should know at least a bit of GDMT thing. So it saves money, and it gives a bonus tolerance as well, and it ensures a design dimension tolerance requirement as they relate to the actual function. So, and also it ensures the interchangeability of mating parts at the assembly and provides uniformity, and it is universal understanding of the symbol of instead of words. If you are having simply verbal, so we have two types of communication normally. One is verbal communication and one is non-verbal communication. Verbal in the sense the speech that what I am giving now that you can hear in terms of words. That is verbal communication, and another one is non-verbal communication, which is a graphical representation. The things that what we're going to see and we're going to replicate in terms of sketches or graphic symbols. So that is what we call as non-verbal communication. So GDMT will comes under non-verbal communication with the dimensions. Little we're going to have verbal communication as well in terms of numericals and a few with nodes. And here ensures interchangeability of mating parts at the assembly in the sense, suppose if you, as I mentioned in the beginning itself, we have, suppose if I take an example of bike or car or bicycle, for time being I will take an example of bicycle itself. Suppose if you have 8 or 10 parts in a bicycle, all these 10 parts will going to be get assembled in assembly section. But while getting assembled, each and every part will not going to have the exact dimension. Definitely it will going to have variation in the actual size. So then what will happen? Each and every assembly, while doing the assembly, you will going to have that part number in that part section itself. So while taking that into an assembly section, you will going to have a continuous checking with respect to the assembly of the cycle that what you will going to make, whether it will going to fit into that particular product. Suppose if it is fitting, then accept it and then move it. So interchangeability is nothing but it will be having a tolerance limit acceptance, so that you will going to have a product output with respect to the assembly and sub-assemblies. So when to use GDMT? When parts features are critical to a function or interchangeability. As I just mentioned the example of bicycle itself, even if you take car, or so why I will take always the automotive sectors, because it is very easy, and also each and every person has a knowledge of automotive and all the transportation vehicles. So then When functional gauging is desirable, even the functionality is required, and when datum references are desirable to ensure consistency between design, when standard interpretation or tolerances is not already implied. So all these parameters come into picture when we need a GDNT, when it allows a better choice of a machining process to be made up for production of a part. That means we will going to have a proper GDNT. So we will have a varieties of GDNT applications that we will going to see in further. And in GDMT, we are going to use a few terminologies, that is maximum material condition, least material condition, tolerance, allowance, and basic dimension. What is maximum material condition? One thing I will always say, that the verbs or words, what we going to listen or we going to see or we going to read, that words itself will going to have a meaning behind it. So just observe that maximum material condition, we're going to have a material condition which is very maximum. So if you have a comparison, so in GDNT we're going to have a shaft and hole as a base concept. So with respect to that, largest shaft and smallest hole. So for that condition, we're going to have a maximum material condition. If you have a 25 mm diameter, if you have a variation of that, so 26 is the largest shaft and smallest hole is the maximum material condition. So least material condition in the similar manner. So it is just the reverse of the thing that what I have said, that is smallest shaft and largest hole. So and then tolerance is nothing but the difference between these two, that is maximum material condition, least material condition in a single dimension. If you take that difference, then you will going to get the tolerance. Allowance is the difference between the maximum material condition of two mating parts or minimum material. So that means you will going to get the minimum clearance or maximum interference fit. And one more important thing that I forgot to tell you, that is fits are very important while understanding the GDMT, because if you are having assembly and sub-assemblies, definitely you must know what type of different types of fits will come into that particular assembly. That means if you are having three types of fit, as I mentioned, one is a clearance fit, transition fit, and then interference fit. So where exactly it comes under that? So that we're going to see. So now, and then basic dimension, that is a nominal dimension or base dimension. As I mentioned, the shaft with the 25 mm diameter, that is a basic dimension. Plus or minus that part we're going to give, that is a tolerance. And again with if you have 25, so that we see in detail with respect to this example. Limits of size, as I said, different types of limits. So here the size dimension. So what does this mean? 2.007 and 2.003. So this is a diameter symbol, and you can see the notations. So here you are having an axis, and here also you are having the center line. So this is how exactly the geometric dimensioning and tolerancing will going to have a communication with the users. That means if you are having a drawing, the drawing should communicate with you. That means the production guy, or it may be a design guy, who exactly will going to see that particular drawing. That drawing itself will going to have a communication with that particular person, and he can understand that particular drawing and what exactly it is and what exactly he has to make on that particular product. So what does this mean? 2.001 so is a maximum material condition. You can see, so this is the maximum material condition of the shaft, and least material condition of the shaft is 2.003. So the variation between these values, so this zone, what we call as tolerance zone, the maximum material condition, minimum material condition. So that is also called as the envelope of size. So we have a difference between the two values. So this is a tolerance zone where exactly we're going to have the acceptance of this product. That means if you are manufacturing, simply this shaft will going to have a casting, and then we're going to have a machining, that is by with the help of turning and facing operations, we're going to complete this product. So while doing within the limit of this zone, if it comes under, then obviously we're going to accept this component, and then we're going to send it to the further usage. So here I have two examples, that is as I was mentioning, that geometric tolerancing. So this geometric tolerancing applied to an angle block. So this is just an example that what I have taken. If I apply the GDMT, by seeing these all these symbol, you will gonna have. So what all these symbols and all those things. Initially, you may think that it is a little bit confusion or it may be a difficult. It's not like that way. So as is said in the beginning itself, you will have a circle, you will going to have a diameter for defining the circle. If you are having a rectangle, you will going to have a length and breadth for defining that particular profile. So similar manner, here you have like this profile. Then obviously you will going to have a dimension, length, and then angle. So this whole will going to have diameter. As I said, this is upper limit and lower limit. So we have a tolerance here, and this is the position tolerance what you are seeing. So feature control frame, and here the encircle of the dimension that what you are seeing is a basic dimension. Always when you use a position control feature system in GDMT, we will always use the basic dimensionings, so that we have to provide. With respect to this basic dimension, the other respective dimensions will going to follow. And with respect to the dimensioning and all, one more important thing, that is datum also has to be defined. That we'll see further one by one in detail, so that you can have a better understanding. And for that same angle block, so here the limit tolerance has been applied without having geometric tolerancing. So this is just a limit tolerancing, as the name itself says, it has a limit. In earlier stage it was having only 2 mm, and this is 2 mm with plus or minus value, that is a tolerance zone or tolerance limit, you can say. So this is just giving geometric tolerance with limits, and this is with geometric dimensioning and tolerancing with the position control system or feature control system. So here limit of size, as I was talking with respect to the maximum material condition and the least material condition. Here, as I said in the beginning itself, it is having different types of fits. So here you have a clearance fit likewise. So least material clearance. That means for the nominal size that what you have with respect to the shaft maximum diameter. And if you come here, the allowance for maximum material condition is the nominal value of the shaft. That means base dimension. If I say 25 mm shaft, the 25 mm is a base value, and plus or minus is limit or maximum and minimum limit value. But here for maximum material allowance, we're going to have a nominal base, and then here we're going to have the maximum size of the hole. That difference we're going to call it as maximum material clearance allowance, and here and the least material condition clearance. And limits of size, as you see, so the shaft will go. So these are all the notations. As you can see that here to define a shaft, we're going to have a center line, and as you can see the hatching, that hatching indicates the section. So as you can see here with the phantom lines and the direction of arrow, where exactly you have cut the section and you are saying it. That means you are seeing from this end. You have cutted this portion and you are seeing from this end. So that's why. So here we have the notation. So all these are geometrical representation. By saying this itself, we're going to say this as a left side view, left of section view likewise. So maximum material condition and least material condition. And limits of size, as I said, why we need this tolerance zone? Just as I said, here we have taken example of shaft itself. So the shaft, while doing manufacturing, it may take any deviation with respect to the length, or it may be with respect to the diameter. As you can see, we have 4 different varieties of shaft that has been manufactured. It may be a bored, wasted, or barreled, or tapered. But still, all these shafts are accepted after fabrication. Why? Because we have given the maximum material condition, or least material condition, or simply tolerance zone. So within that, if it comes, definitely we're going to accept the product. But with respect to the functionality concern, then it again concern we're going to have the variation with respect to the different assembly parts again. And other factors, that means parallel lines. Suppose if you have edge. If you are having an edge or line like this, then definitely we're going to have a comparison. So we're going to have a parallelity, perpendicularity. So here we have that parallel zone. So suppose if you are having a circular shaft, we're going to have a tolerance zone like this. If you are having a surface or line, it will be like this. If you have a profile, you will going to have a parallel line like this. This all parallel lines, that what you are seeing is nothing but a tolerance zone. That means we're going to have upper limit and lower limit to accept the component. As I was talking about the 14 characteristics, so that is very, very important. So the 14 characteristics are, as you are seeing the screen, so we are having these 14 characteristics. That is simply, you can simply call this as alphabet of GDMT, because even in the interviews or in industry, definitely they will going to ask you as a fresher. If you are attending an interview, definitely they will going to ask you regarding GDMT, these symbols and all. So we have different segments. So all these 14 symbols have been segregated in 5 different tolerance types. First one comes under form. As the name itself says, the form, that means how exactly the profile shape is there. So it is a form. It may be either flatness, or it may be straightness, or cylindricity, or circularity. So what exactly this form is all about? If you have a pen or if you have a rectangular block, so that also I will going to tell you in future slides, but still I will just give you a brief overview of this form type. So flatness is if you are having a cell phone itself, as you are watching, a few of you might be watching through cell phone itself. That cell phone or that mobile will going to have the touch screen. So the entire screen will be considered as a flat surface. So we're going to find out that flatness. Straightness in the sense that entire screen that what you are having on your hand, the edges that what you have, that is a straightness. The edges has to be maintained with the straight, and the surface has to be maintained as flat. And then cylindricity and circularity as concerned, we're going to have this cylindricity and circularity as similar to the flatness, that is shaft. So exactly at the end of the shaft, we're going to have the, I will say with respect to the cylinder. So at this end, that means the circle will be considered as a circularity, and the whole length, if you consider, that will be a cylindricity. So in the similar manner, so the forms will not going to have any relationship. That means the flatness will not going to take any reference. So we're going to take that flatness without having any relationship. We're not going to correlate with whether it is having a flatness or not. So with the help of what the flatness plate, normally you might have checked it in your engineering. So we are having CMM and plenty of different inspection tools. So even here also straightness and cylindricity, circularity, all are not having any requirement related to the relationship, because those are not having any inclination or orientation. So then with respect to the orientation, so now it comes into picture. Next tolerance type is orientation. That is perpendicularity, parallelism, and angularity. That means to say the perpendicularity will come if you have one reference. So that must be having an angle of 90 degree with respect to another, as the symbol itself portray you. So by seeing the symbol itself, you can have an understanding. That's what I said. The symbol that what you are seeing in this column is a non-verbal communication, and all these words that what you are seeing, these a verbal communication. So both these are required. So both of them are required to have a better communication and to have a better product output. So orientation, so that is having 3, and then location. With respect to the location, that means if you are having a different holes on any rectangular block or any shaft as a keyway, so at that time we need to have a position of that particular hole or any slots. So for that we need a location. So we're going to use a position geometric symbol. So and also profile of a surface and profile of a line. As I said, to with respect to the cylindricity and circularity, it is of same kind, but with respect to the surface in the sense. So here only, so this is a profile and this is a surface. This entire surface, if I consider, that will become a surface, profile of a surface, and if I take just an edge or a line, that will become a profile of a line. And then total runout and circular runout, that will come for especially for shafts. So total runout and runout, so as I said, for circularity and cylindricity, we're going to have the shaft here. If I rotate from one revolution, or if you give one revolution here, so exactly at this edge, if I keep a dial indicator, then it will going to have one rotation, then we'll want to check the deviation. So at that time, what is the deviation, we're going to check it, and then we're going to have one more revolution. Likewise, if you keep on doing it, so without having any errors, we're going to have circular runout. Total runout is nothing but by taking this number of rotation at a different position for an entire cylinder. So then we're going to have a total runout. So we're going to have a better understanding of the entire profile. Then we have the concentricity and symmetry. So next, we have other different characteristics and symbols as well. All these also has been used in geometric dimensioning and tolerancing symbol. So with respect to the different applications again, so this is our diameter, tangent plane, free state, so maximum material condition, least material condition. So all these are just like an alphabets. They will going to be used for particular applications. So if I take an hierarchy of GDMT, as I was talking about the 14 characteristics and 5 forms. So 5, that means 5 different types, tolerance types. So if I take a hierarchy of that particular different types, form we're going to give, we're going to have just a profile or a surfaces. But if you consider the orientation, by taking the orientation itself or by defining the orientation itself, we can control the form. How? If I give an angularity, definitely we're going to have a reference. If I give an angularity, definitely we're going to have a reference. Then we're going to have this lines. For this, we're going to have a tolerance. So definitely what will happen, we're going to control the straightness and flatness as well. So that is how we can give or we can control the form and the orientation. Now, if I move further, the location, with the help of location itself, we can have a control over orientation as well as the form. So likewise, we're going to have this kind of hierarchy. So we can give a location. Now, most of the cases we'll always have the position control feature system. A feature control normally we can call. So position controls or location controls are now most widely used in GDMT of manufacturing of any product. So this is what I was talking about, the feature control frame. So we here we're going to have a geometric symbol, and here we're going to have a tolerance information, and then we have a datum references. So all this we're going to have a discussion, because if I keep on saying like this, you will not going to understand better. So I will give plenty of example, and I will give each and every information in detail. So this is the geometric control tool, and this is where the tolerance zone will going to come into picture, and this is the datum reference frame definition. So we'll always have a datum to define, and we're going to have a tolerance zone, and we're going to have a feature control frame. So all this will be used with the help of different applications again. So for whether you are having a caster product or machine product, whether you are having a sheet metal product. So nowadays we are not using a sheet metal. For sheet metal, we normally not going to use GDMT, because we're going to have a laser cuts, but there we're going to have a tolerance itself. And we have a casting and the machine product. So blending of casting and then machining operations. So again, there we're going to have projection modifier, free state modifiers. So likewise, so different modifiers also has been used. And as I was talking about datum reference symbols, so normally we have these reference and symbols with respect to the different standard that what I was talking about, ANSI 1982. So the datum reference will be having it like this symbol, and the ASME will going to have 1984. So we're going to have this type of symbol, and similarly ISO. So placement of datum. So datum. So while having complete a GDNT in any drawing, first of all we must understand any diagram will going to have a datum first. That means reference. What is datum is? So datums are generally placed on a feature on a center line or a plane depending on how dimensions need to be referenced. That means if you want to measure anything, you must have a reference line or reference surfaces. So those are called as datums, references. So that may be a flat surface like this, or it may be like this, or it may be like this. So what it is saying is you can either use feature on a feature, either you can use a center line. If you are having a circular object, normally we're going to take the center line as a datum in few cases, and also for with respect to the holes, and also with respect to the planes and the flat surfaces. So the placement of datum, as I just said about that. So feature sizes such as holes. So normally we're going to call the datum E for this particular hole. Though the datum has been defined for this hole, we're going to take the axis as a reference, and we're going to have the tolerance here. We're going to have a 0.5 diameter hole here, and with respect to the upper and lower limit. So with reference to this, we're going to have the manufacturing. So here we have a maximum material condition as I was talking about. So this is a position control frame. Here we are having a diameter with respect to the tolerance zone, and here we're going to have a modifier that zone. So here we're going to have a bonus tolerance as well. So when you are having modifiers, so then we have datum. So we're going to define this datum, and we're going to have all this. So if you have any object or product, then we're going to have different degrees of freedom actually. So while making that, or while understanding the different degrees of freedom has to be arrested, because if you keep on moving, then you can't have the measurement while having in motion. So that is why we must arrest the moving object. Instead of having a dynamics, we're going to have a static. That means at rest condition, you can easily measure and you can take the dimensions and all. So that is why we must arrest all the degrees of freedom. Then we can have better observation on that particular product. So to and fro motion, if you consider, normally we're going to have 6 degrees of freedom for any 3-dimensional object. But if you consider the to and fro motion as well, it will become 12 degrees of freedom. So as I said, how exactly the datum has to be defined. So when you are having a product, so as I said in the while having the conversation, if you are using a mobile, if you are having that mobile itself as a product now, so the datum has to be chosen. So how exactly we want to choose the datum? That is important, because as I said, and today's session will go, what we are talking is a key aspect that what the quality and the design will going to happen through this GDMT. So just by seeing that mobile itself, just have a glance. We're going to take the primary datum, secondary datum, and tertiary datum. That means you need a reference to measure that particular product. So for that, what we need to do, we need to choose a primary datum and secondary datum and tertiary datum, where exactly we're going to have that degrees of freedom has to be blocked, so that you can measure the distance with respect to that datum. So how to choose a primary datum, secondary datum, and then tertiary datum? So we normally call that as a 3-to-1 principle in GDMT. So how 3-to-1, and what this 3-to-1 is? We're going to have a major or a larger surface where you're going to have more functional features. So that will be a primary datum. That means where exactly we're going to have a larger feature. Or suppose if you take that, normally we're going to take that particular as a primary datum, and then we're going to take the secondary datum with respect to the other surface, and then tertiary datum. So plane A, and then plane B behind, and then plane C. So now this body can't move on either three directions. Okay, even it will not going to have any rotation as it is a translatory object or a prismatic object. So here we have arrested all the degrees of freedom. Now you can easily measure with respect to the datum what is the height, with respect to the B what is the distance, and with respect to the C what is the distance. So in all the three views, if you measure the dimension, obviously what exactly that product is all about and what are the different dimensions it is having, whether it is a good product or not. So everything you can take it out. So you can just have a glance on your mobile itself. You're going to have a base as a datum. Touch screen will become parallel with respect to the datum itself, and then side edges, that is larger length that what you have will be having a datum B, and a smaller length width what you have that will be datum C. So as I was just talking about, you just assume that this is your mobile. So the base will going to have plane A, and this will become a plane B, and then this will become plane C. So likewise, we're going to restrict or rest the degrees of freedom, and we will going to measure the dimensions. So this is the angle of projection that what we have. So by seeing this diagram, you must be in a position as being a mechanical engineer. You must be in a position to tell the degrees of freedom by seeing this itself. So this is third angle of projection. And then, as is just said, the secondary and tertiary datum will be chosen in the similar manner with respect to the feature that what you have selected for primary. Secondary and tertiary datum that what you will going to choose, that must be a perpendicular to other two datums as well. Now, so this is in detail again. So while having the degrees of plane A, so we're going to arrest 60 degrees of freedom, and then after defining second datum or secondary datum, we're going to arrest 10 degrees of freedom. As I said, we're going to arrest 2 degrees of freedom. So with respect to 1 degrees, if you consider to and fro on both the ways, so we're going to have 2 plus 2. So likewise, so we're going to have 10 degrees of freedom arrest. Next, we're going to have a total 12 degrees of freedom arrest. So this is how exactly the symbol we're going to use while choosing the datum. So the plane A at the base, here we're going to use this encircle of A with respect to ANSI symbol, and here datum B, and then we're going to have datum C. So this is the CMM that I was talking about. Nowadays we are having the laser technology and the scanner technology, that what I mentioned in the advanced reverse engineering session. So we are having the advanced scanner and inspection tools nowadays. So CMM is one among them. So it's not a tough job nowadays to have an inspection with respect to the earlier days that what we were having. So next, the size, that is very, very important here. If I have a defined datum, so this is on the drawing. On the drawing, we're going to define like this. So we're going to define the datum here. We're not going to directly give to the axis. We're going to define to the surface which is parallel to the axis. That means the datum, what you have defined here, that may be having variable profile like this, but it should come within the tolerance limit. So this is the datum axis. Observe here is the datum axis, and this is the smallest circumscribed circle. So it may have variation, but still it has to maintain proper profile. So it should be within the tolerance limit. And here also. So this is the largest inscribed circle. That means here the smallest inscribed circle. So this shaft will be a smaller portion. So here this will become larger. So at that time both the cases will going to accept the component. Either the hole may have variation in the profile, or the shaft may have variation in the profile. Finally the assemble has to happen properly. So that is all about that what form conditions actually. Till now that what we have seen, those are all form conditions, and now we'll move on to orientation tolerances. As the name itself says, the orientation. How exactly the object is oriented or the surface is oriented with respect to other surface or other datum. So likewise, perpendicularity, angularity, parallelism. We're going to have here. We're going to have a relationship. So you need one datum initially. So for giving a perpendicularity, definitely you need a relationship. So it is a relation based tolerance type. So perpendicularity, angularity, parallel. So how exactly we're going to define the perpendicularity? So we're going to define either this surface or this surface or this surface. So while having an object, one simple common sense you can adopt here, along with the a number of features that what you have, that feature will be defined as a primary datum. But still here we're going to have a base datum as where exactly that component will going to rest. So normally that will be taken into account. And here we're going to have a perpendicular symbol, and then we're going to have a tolerance zone with respect to the datum. What exactly it is? Just observe here. So the A that what I have given as a datum will going to have a variation in the profile. So this will be a datum B actually, but as per tolerance zone concern, even the variation of this profile, if you are having like this, because if you go to micro level and nano level, obviously we can see the surface like this. In normal eyes, we can't able to see like this, but definitely we're going to have the variation like this. If that particular product is coming within that tolerance zone, obviously we're going to accept the component. Only for quality inspection. So how exactly the design has been made and how exactly the GDMT is making a very vital role while accepting, while moving a quality products. And here also the same thing. So here we have position control. So but without having any modifiers. So here the datum has been defined with respect to this diameter itself. So this means the whole axis must be perpendicular within a diametric tolerance zone of 0.1 relative to the datum A. That means to say the perpendicularity has been given. This is first so this is the feature control system. First we're going to give the diameter with respect to the tolerance, upper limit and lower limit. For a diameter of 2 mm diameter circle, we're going to have upper limit and lower limit, that is the tolerance zone that we normally give. Then we have this geometric tolerance. So this geometric tolerance is for axis. So just observe here, you will going to have maximum material condition and minimum material condition for this particular shaft or hole. Then you have geometric tolerances as well. Definitely what will happen, you will going to have a virtual condition and then bonus tolerance. That I will tell you for the slides. So here we have the orientation. So this should comes under tolerance zone, and this should not have any deviation with respect to the tolerance zone that what we have specified as 0.01. So then we can accept this particular product. Even in relation with respect to the angularity, as I said, we must define a datum, then we can give an angularity. So for this particular product, we're going to have datum A, and then the orientation of this surface with respect to this datum is 45 degree. So just observe here. So we are not having any diameter or any other circular profile. So simply we are having a surface. So angle, we are giving an angle. So that will be mentioned or defined with respect to encircling of this. Okay. So that will say a basic angle. So that basic angle will be defined. And here we're going to have an angle with respect to 0.05. That means this line can have a variation in between this zone. So while manufacturing, this may have an enlargement towards this, or it may have deviation like this. So it may have any profile, or it may have a profile like this also. If that comes within that tolerance zone that what we have specified, obviously we'll want to accept the component. Why? Because so that is why GDMT is not only giving a manufacturers freedom for accepting more and more components, rather than rejecting a component and wasting manufacturing lead time and as well as labor charge. So it is always better to go with the GDMT. So now parallelism. Similar to that angularity, perpendicularity, so the parallel is same. So you're going to have a we'll define datum first, and then we're going to have a parallel symbol, and then we're going to give tolerance zone value, and then we're going to define the datum. Here also we're going to have 2.5 plus or minus 0.01. And if this line or this edge comes under with tolerance zone, accept the component and wait for the. So that is about the orientation, and then we were talking about that maximum material condition and least material condition regardless of features size. So normally we're going to say maximum material condition, least material condition for shaft and hole. So because any assembly, if you consider, normally we're going to have a hole or slot, either it may be of any kind of hole, either it may be a normal through hole, or it may be counter bore hole, or it may be counter sink hole. So we're going to have different types of maximum material condition and the least material condition. So how exactly we're going to define that? For shaft, we're going to have a maximum size. So this is maximum material condition. For hole, we're going to have the maximum material. So minimum size, that will be a maximum material condition. That means to say, you may be having a confusion. How exactly? So maximum material condition in the sense, you're going to have a shaft of 25 diameter. Suppose if you want to reduce it for 23, if you want to achieve, normally after casting, you're going to have heat treatment, and then you're going to have a machining of that particular shaft. That shaft will be reduced with the help of lathe machine, and it will be turned. So while turning, you will going to have maximum of 26 base initially when you engage it into the lathe machine. You will going to have 26 mm diameter. After machining, you will going to have a reduction of 23. Suppose if you are having expectation of 22. Suppose if you have stopped at 23, you will be having a provision to reduce one more mm. That means to say that is a maximum material condition. At least that would be better. If you are having a maximum size, you will be having a provision to reduce one more mm. So suppose if you have a hole, if you have already drilled a hole of 25 mm, actually the intention of creating that particular hole would be at 25 itself. Suppose if you have already drilled a hole of 25, and suppose if you have increased it further 25.1, then definitely you are not going to have a material to reduce or to create a hole again. So what happens? You're going to have a continuous loss of material. So the stock will be there. That means the material should be there, so that you can have a better provision for either creation of hole or reduction of material with respect to the creation of shaft. So in the similar manner, we're going to have regardless of feature size. That means if you are not using any, or if you are using, or if you are not using modifiers, then we have regardless of feature size. As the name itself says, we're not going to have any feature size as concern. So regardless. So in maximum material condition, how exactly we're going to consider? We're going to have maximum material of shaft is the largest allowable size. So we have all these thumb rules, and we're going to incorporate for these kinds of application. Where exactly these are used means the size such as hole, slots, pins. Because each and every component will going to have either integrated product or it may be assembled. Any of the kind, you will going to have different types of fits, and also joints. Either of any type of joints you may have, either it may be through suppose if you have a permanent joint, that will be through welding, or it may be suppose if you have a temporary joint, that will be through fasteners. That means if you are having number of components, as I mentioned earlier, the automotive components, car, bicycle, or bus and everything. So all these will going to have different number of components, and they will be get assembled with the help of these boards, nuts, slots, everything. So at that time we must need maximum material condition, least material condition, so that we can have a perfect fit, either of any type, three types of fits we can have, and we can have a very good functionality with respect to the product concern. So as I was talking, maximum ideal condition, this is when part will weigh the most. That means you're going to have maximum material stock. So you're going to have that condition. And here least material condition, that means you're going to have less weight. So length for shaft is the smallest allowable size. So we're going to have smallest allowable size. As I was talking about the reduction and the whole enlargement. So that is how we're going to have larger materials or least material condition and maximum material condition. So regardless of feature size, that is simply we say that as RFS, that is requires that the condition of the material not be considered. This is used when the size features doesn't affect the specified tolerances. That means this is also again used for hole slots and pins, etc. So then we have location tolerances: form completed, orientation completed, and now location tolerance. So as I was saying about the hierarchy, the orientation will going to give form as well. Now the location will going to cover the form and the orientation as well. Here the position, concentricity, and symmetry. So these are all the these three are the location tolerances. As this position symbol so says that location. So as previously with respect to the example you have seen, and the concentricity and symmetricity. So rarely we're going to use, but most in almost all the GDMT. So this is where you will going to see the symbol. So position feature control system is very widely used in all the different types of sectors of manufacturing process. So for datums, so we'll just take a few examples. So coordinate system position. That means why we were talking about geometric dimensioning tolerancing. So as I said in the beginning itself, you're going to have geometric dimensioning for a particular circle radius or diameter. For a square, you're going to have length and breadth. Likewise, you're going to have a geometric dimensioning. And then we had given a tolerance for accepting the product after manufacturing. So here, what is the use of doing by giving the tolerances? So if you just see this circle, if I give a tolerance for this, just see this portion itself. We have 2 plus or minus 0.05. If I add this 2.005, we're going to have the extension of this position. The whole position will be having an extension like this. That means upper limit and lower limit. It will create a rectangle section at this portion. That means this position can have a variation with respect to the square portion where you have. That means either, so this shaft, actually this is a shaft in this section. So across the shaft we are having a hole. So here you will going to have a provision for what this slot, and you can have this slot position within this boundary. That means if I 2.005, it may have 0.005 this side or 0.005 this side. That means you will going to have two boundary, and for this dimension also you will going to have upper and smaller boundary. So that will create a small square. Within that, if you are having this whole position, if it comes under, then definitely we're going to accept this component. So likewise, so this is how the geometric tolerance or GDMT is very much usage, because we're going to have that much of freedom to accept the
Excuse me,
component.
sir.
Yes.
I think your screen sharing is stopped. Could you please-
Okay. Yes. Visible, right? Okay, so this is how we exactly will going to have the what usage of GDMT, which comes within this square zone. Suppose if you position control system, so we're going to have, instead of having this square, we're going to have a circle like this. Means to say the whatever the portion we have this portion, so that also will be get accepted while manufacturing the component. That I will tell again. So here also, so this can be accepted. So here I will just explain with this example, position tolerancing. Consider the same hole but add GDMT. Suppose if I add GDMT, that is position control feature system. So here for this rectangle, I have a hole here and have a base dimension. So while giving position control or feature control system, first you must give a base dimension or basic dimension. That basic dimension should be encircled like this always. So that will be a basic dimension or base datum. You can call those dimensions as a datum dimension itself. And then we're going to give diameter with respect to the tolerance. So, and then position control with respect to the position tolerance with respect to the maximum material condition, and you have the datum here. So like this, we're going to have position control. Here we have a provision. So observe here. Here we have a 0.01 tolerance zone for this center. So instead of having rectangle portion, suppose if I draw a rectangle here, you will not going to have the acceptance of position where exactly in the circle that what you have. If you have a rectangle here, only this position will be shifted within this rectangle zone, but you will not going to have a provision to accept this portion that what has been missed. So that is why we're going to give position control system, so that whatever the remaining portions or empty spaces that you have missed with respect to this position circle, that will be accepted. That means instead of rejecting more components, you will going to have acceptance of few more components by giving GDMT. So that means, so normally in small scale industries, so while giving the GDMT symbols and the manufacturing, they will be a little scared if you are having a GDMT. But truly speaking, if you have a GDMT, we will going to have a plenty of liberation or liberty with respect to the manufacturing and with respect to the dimensioning. So you're going to have more space to accept the component instead of having the rejections. So that is what the bonus tolerance that I was talking about. So with the help of the modifiers, so we're going to get the bonus tolerance. That means, as I was talking, the circle will definitely going to have 50.003 maximum limit, and if you have 47.007, so that is a minimum limit. That is a tolerance zone, and again you have position tolerance zone. That means this geometric tolerance and this tolerance zone, so both will be get added, and you will going to get the bonus tolerance of. So always when you position control system, you're going to get the bonus tolerance, as I just mentioned. This rectangle slot that what you have seen in the previous slide, the portion that what we have missed out, so that will be a bonus tolerance when you use position control system with respect to the GDMT. So that is how exactly in industry they are using, and we are having the complex GDMT stack up analysis. So many things are there. So this is what I was saying you guys. So this is what the diameter tolerance zone, and you are having this small portion of bonus tolerance as well. With the help of that, you can have a provision for accepting these kind of values. I was sorry, it was not a 50. It is a 0.497. So we are having a different variation of combination of this value also with the help of this value. So we're going to have more number of acceptance instead of rejecting the component with respect to the position tolerance that part we have given. So here also, if I take that, so we're going to have 0.497 if you are having a hole. If you are having a position tolerance zone, that is a bonus tolerance zone of 0.01, So then we're going to have the upper limit of this plus subtraction of that, and with respect to this we're going to give a 0.02 is will be the bonus tolerance. That means 0.01 and 0.01 if you add, so it will become 0.02 with respect to the tolerance zones. Similarly here also. So like this. And then at last, virtual condition. So as I was talking about the tolerance, different types of tolerances and all. So this is at last, that means GDMT is actually just like an ocean. You have plenty of things. Whatever the things that I have just spoken, it is completely related to basic mechanical operation that what we do. That means it doesn't mean that it is only stick to mechanical engineering field. As I said in the beginning itself, it is also applied for civil engineering and electrical and electronics background as well, but of different standards. As I said in the beginning itself, we have a number of different standards for different applications. For civils, they are using different standards. So normally for building sector, BAS, BSLS, so or different vibrations analysis are like that. So each and every engineering disciplines has their own standards. Even for electrical and electronics, they are having a wire harnessing. As I mentioned in the automotive sectors and aerospace sectors, obviously each and every car, bike, everything will going to have electrical circuit. Without electrical circuit or without having a battery, you can't move. Only with the help of engine you can have, but still at night you can't have a motion without having any light. So you need a battery, and for initial ignition and just for self start everything. For that you need a circuit. So in bike, in car, in aeroplane, in all the transportation vehicles, and even in the house, we need electrical circuits. So circuit diagrams, and also in civil engineering. So we have what elevation plans, everything. So each and every what engineering fields has their own importance and application of geometric dimensioning and tolerancing with respect to the different application. As I said, in civil engineering also we have HVAC, plumbing. So likewise, so it is a little interdisciplinary with respect to mechanical. And again, if you comes under electronics, so we have electronic circuit boards. As I mentioned, we are having electrical wire harnessing in aerospace industry, automotive industry, and automobile, that is the bike industry. And now we are having evolution of EV vehicles, so we're going to have very good scope for electrical engineers as well. And GDMT is not only stick to any particular field; it is a language of a drawing that has to be incorporated or that has to be learned by all the engineers, so that they can have a better manufacturing process. And also while designing, so you must know what exactly the process will going to happen. As I said in the initial slide itself, I have shown you guys that design and tooling both are very, very important in any manufacturing industry. If you don't know about any designing aspect or tooling aspect, that means you must know the production process as well as the production procedures. Then only you can have a better hold on a design tools, that what I mentioned in the reverse engineering process. So advanced reverse engineering session. So here the virtual condition, that what I was talking previously, we were having a tolerances zones. So here that means to say we're going to have the virtual condition, that is maximum material condition plus geometric tolerance. That means to say we're going to have a position control feature frame here. So we're going to have position. That means we're going to define the center line will be as a datum or reference. So for this center line, we're going to give a position control of 0.01. That means to say 0.01 will be a tolerance zone. So if this circle will comes within this, either it may be having a little inclination with respect to this, like this, or it may be a wavy like this. So you can have an acceptance of that particular product with reference to the datum that what we define. So that is virtually will going to happen. So why So the name itself says it is a virtual condition because of maximum material condition, least material condition, and then position control frame with modifiers, as I said. So these are modifiers. If you use that, then definitely we're going to have virtual condition. Since there is no material modifier here, as I was talking about, regardless of feature size, that means either if you may have a shaft or you may have a hole, either of two cases. Suppose if you have a modifier in the sense you're going to have a maximum material condition or least material condition. If you don't have it, as the name itself says, simply regardless of feature size. So we're not going to bother about the diameter of the shaft or diameter of the hole. Then we'll going to call that as a regardless of position feature control frame. So this is about the virtual condition. And I hope I have covered all the things that what we need to know before understanding the concept of any production or design. So these are all the aspects that you have to understand properly so that you can have a better information or a better hands-on experience while doing any design and any production work. So in industry, each and every person must be known. Suppose if you are a mechanical engineer, if you want to go for any design jobs, or it may be production or it may be quality, you must know about the GDMT, because one or either day you must see that drawing. So you must understand these concepts. So in that layout in the beginning, I have what I have shown. So here, so you can see, so each and every person are interrelated, that is connected. As I said, this is a concurrent engineering. So one and other person at least should know about that drawings and all, so that you can have a better interface and better communication, so that you can have a very good product life cycle stability, so that you can sustain in a market, as I said, in the product life cycle. So this is what complete GDMT and its importance in industry. And this is what I was talking, and in between slide I have missed that. So as I said, the hierarchy of the 14 control characteristics, that is form. So it controls the shape of the given feature. As I said, suppose if you have a shaft, you're going to have a circle and then the cylindric portion. So that is a line, circle and cylinder. So straightness and then flatness, cylindricity or circularity. So that will be controlled with the help of form. Orientation, in the sense, if you have, so the orientation will control both form as well as orientation. That is, as I said, when we were talking about orientation, that is angularity, parallelity and perpendicularity. We're going to cover the form as well as the orientation features as well. That means it will going to cover straightness, flatness as well, along with the angularity, parallelity and perpendicularity. Then we have location. So if you use the location, that is position control frame, so that is widely used, as I said. So how exactly we're going to use these 14 characteristics in GDMT, that is also very, very important. As you get experience with small scale towards larger scale industry, day by day we're going to have a better control over a GDMT, which are all the GDMT symbol that I have to use for a particular application, and which would be better, and which are all the characteristic symbol will going to have better control over others. So even in the interview they may ask you, so how exactly we're going to have a control over concentricity or cylindricity, or so how can you overcome from those 2 or 3 features. So likewise, so and if you give a runout, you can have what cylindricity as well as concentricity as well, and also the position. So all the 3 can be controlled with the help of runout itself. So by giving one feature or one GDMT symbol, we can have a control over many features or many profiles. So likewise, so only the thing is you must have a ground experience. Then only we're going to have a better control over all these features and control over that GDNT symbols. How exactly we're going to incorporate that is of different case. And I think I have covered all the basic fundamental details that is required for a fresher and also for an experienced person of how exactly GDNT we are using in industry and how exactly we had to adapt to the drawing. Along with this, we must know about angular projections as well. And okay, so I think I have covered everything. Fine. If you guys are having any kinds of questions on whatever the thing that I have just discussed, suppose if you want to know about any other scope related to the GDNT with different disciplines, so please, you are open for questions, so you can ask.
So there is a question in the chat box that is, what is unilateral and bilateral tolerance? From Mr. Raghavendra Nagar.
Shaft, if you are giving a dimension on only one side, so as the name itself says, in across the lateral, that means across the diameter. If you give only on one side, it will be a unilateral. If you are giving on both the sides, if you are having a 24 mm diameter that you would like to reduce it for 22, on either sides you will going to reduce in half of the, that means bilateral. If you are having only one side reduction, then we call that as a unilateral. So that is unilateral and bilateral reductions and tolerances. So I am trying to implement GDNT in design application, but I find it hard clearly understand the concept of GDNT. Initially, irrespective of any subjects or any language, normally definitely you will going to have a difficulties. But once if you get into it, definitely you will going to have a better control over that particular subjects. Even when I was being an engineer, when I was studying as being a student like you, even I was thinking in that manner only. But when I have got experience with various different types of industries and research work that what I've made, so I have got an exposure to understand the languages and the features in a better manner. So likewise, definitely we'll also get understand. So what are the basic concept that what I mentioned? So you just go through that and and one more important thing, if you want to understand the GDNT, take a basic shaft and a rectangle block and a hole. So by taking this small component as an example, just keep on writing the dimension, what are all the control frames or the basic dimensioning and position control system, maximum material condition that what I mentioned. Just try to give the dimension for these features, then go for little complex diagrams and go further. So likewise, if you keep on upgrading the diagrams, so then definitely we're going to have neat understanding or better understanding with respect to the subject. So please provide GDNT resource in ASME Indian and ISO standards. Okay, I try to make a small bottle cap with the thread in CAD software and printed in 3D printing, but it makes a loose fit output. Obviously, as I said, you must know the tolerance zone, as I mentioned. So if you are creating a thread or cap, though you are having a 3D printing anil, so you may have a handy sketch also. So, but if you want to get a better product or better assembly, then you must have an engineering application for that particular product. You must have usage of GDNT properly. If you have a tolerance zone, then you can play with any product and manufacture. For GDNT resources in ASME and DIN and ISO standards, you're going to get plenty of materials in online actually. So you can surf. You're going to get plenty of PDFs related to ASME standards and ISO standards. In reverse engineering, while making soft copies, geometry from actual figure, what precautions to take care? So in reverse engineering, to make a soft copies, one is you must have very good scanners properly. So if you have sophisticated scanners along with the product that what you have, that also should be in a good condition. Suppose if you are not having, because some scrap product also will going to have a scanning. So at that time what we have to do, so we have to scan each and every coordinate points properly, otherwise it is very difficult to have a recreation because some features maybe get missed. So and if you have at least a little capturing points of that particular profiles, then definitely you can have a physical look on that particular product, and with the help of or with the reference of that particular feature, you can create exact feature or size. Okay. Especially GDNT in the point of view of GDNT. Okay. So in the point of GDMT, when you are doing a reverse engineering, as I said, reverse engineering of different methods we have. In the last session that what I have taken that is related to advanced reverse engineering. Now we are having sophisticated scanners software. So it would be better if we have very good scanners. It will be very easy for us to scan each and everything in detail. And then GDMT related concern, that means after converting that scan data into a step model and the CAD data, before giving it to the manufacturing, suppose if it is a cast product, just to take an example of mining product, that would be having a casting process. So there we're going to have different GD&T conditions. So and then suppose if you have a machine components, there we're going to have a different GD&T conditions. And suppose if you are having a sheet metal product, then we're going to have a different geometric dimensioning condition, not GD&T symbols and all. So likewise, so different applications has its own importance. So when you get into the experience, or when you get exposed to the various different types of applications, then definitely we're going to have how to change the standards of various drawing. Standards of drawing from YouTube. How to change the standards of various drawings from YouTube. Okay. So we're going to have a different standards change. That means, suppose if I take an example of a simple rectangular diameter, so we're going to define the dimension with respect to millimeter or inch. So each and every software has a unit system base. There you can have a provision for changing the dimensions for different standards. Either it may be ASME standard, or it may be ANSI standard, or it may be any different kinds of standards. And also with respect to the unit system, all you are having, all the provisions you are having in the softwares. Is it good, sir, if we find product development role but not completely in mechanical domain code design? Yes, obviously, product development is day by day you have to get upgradation with respect to the technology and manufacturing process. Each and every aspects you have to know so that you can have a better new product development or innovation. So you can find out. Should we jump or take that opportunity? Yes, you can. Because as the manufacturing sectors are coming nowadays, you'll be having a very good scope for product development. So you can go for it. And as I said in the previous session also, please upgrading yourself with respect to the technology and the advancement, whatever that is happening in what surrounding related to engineering, or it may be any related to anything. So can GDMT help in point of view of robotics, like robotic arm used in industry? Yes, obviously. Robotic arm, as we were talking about robotics. As you know that each and every industry is in assembly line, they are using the robots itself. Even in the car manufacturing, like Tesla and BMW, Rolls-Royce, they are using plenty of automation tools. All the robotics are being used instead of human resources. So plenty of robotics are playing a role in assembly sections, even in Toyota, in Bidadi, in Bangalore. So they are using it. So as you said, the GDMT is very very helpful for that also. So we are having different kinds of robots. So Cartesians, spherical robots. So likewise, so each and every industry will going to have the manufacturing of that particular robots also. So GDMT is needed for that also. Why it is hard to find design engineer opportunity in aerospace industries? No, it's not hard actually. So you can get an opportunity through aerospace industry. Since from past 10 years, as I started my career in aerospace industry at CN itself. So later I have been migrated to various different fields of industries. So you are having a better scope now. Because of pandemic, little market is slow. So don't worry, you will gonna get a better opportunity related to aerospace industries. And one more important thing is they have already designed so many things, and as a mass manufacturers, if you want to make little modifications, so they will be thinking in in larger perspective. So definitely we're going to have opportunity. Keep trying it. Okay, Anil, I think you have got plenty of questions. I think I have answered for all the questions that what you have posed. Feel free if you have further question. Okay, anyone else has any questions? Could you explain on what products in aerospace industry you got exposure? I was working in Boeing, so I got an exposure for electrical wire harnessing and then air structures. In electrical point of view, tolerance measurements can be done by GDMT server. In electrical point of view, tolerance measurements can be done. Okay, for electrical, so we normally will not want to take that much of account in GDMT. That means, as I said, in GDMT we have different standards for IP standards. So BIS standards we have for especially for electrical point of view. GDMT, as I said, it is for dimensioning and tolerancing purposes. In electrical harnessing, you will going to have installation points. As I was working for aerospace industry, so you're going to have installation points. For that, you will going to have only the wire diagram and everything. There, you're not going to have that much of need of GDMT. There, you're going to have only the dimensions. So positions you need to have. Suppose if you just take an example of your household itself. If you are having a fan, ceiling fan, to that ceiling fan, you will going to have a switch. From that position to that ceiling fan, how exactly will going to draw, how exactly will going to locate. Even in civil engineering, they will going to have that location points. So likewise, you can have that circuit diagrams in electrical point of view. What well-known software mostly used by aerospace and automotive sector? In automotive and aerospace, CATIA and UG and SolidWorks are used. CATIA is most widely used in what Boeing, Airbus, as well as in Bombardier, along with UG. Almost all the aerostructure component that what I have done, that's through CATIA on. So that is a vast software and user-defined software they have given for users itself to customize it. So with the PDM and so VPN network. So if you know that CATIA very well, then you can handle any software, because all other related software, that is SolidWorks, Creo, and UG, are very much easier as compared to CATIA, because in CATIA you're going to have a non-verbal interface. That means to say visual interface. You're going to have a graphic symbol rather than having a graphic along with the verbal, like extrude. In SolidWorks, you're going to have extrude symbol along with the command name. That means verbal and non-verbal both will be the graphic user interface. But it's not the case in CATIA. Could you explain, sir, importance of other skills except modeling to enter into the aerospace industry? Example, simulation. But in India, you are not having that much of scope. Yes, obviously, when you get once into the industry, you're going to get different scope related to what analysis, basic analysis, and even with respect to the simulation as well. Uh, you can go for CAE tools. You can go for structural analysis. You're going to have what visual basics. So you can go with that, because the automation with respect to the FEA and all those things, they are doing it. So you're going to have a scope related to the aerospace industry in those software concerns. That means upgradation, that automation. So you're going to have a scope for automation. Well, I think okay. Yes, Visual Basic only, because in CATIA they are using a macros by using VB. That's what I said. They are giving a provision for customization by user itself. In PMI, how to mention which operation should be done on part. Okay. Any other question?
So Mr. Shambhasigurao Garu has requested for the mic.
Okay.
Hello. Hello.
Yes.
Sir, for some dumb people, like they can't able to speak. For
Yes.
those people, you have to prepare like artificial larynx voice box.
Hmm.
Uh, how far it is possible to implant in such people to produce the normal talking and all?
We have a language actually for them. So, as you know, the advancement of artificial intelligence and all, so we are having the transformation of that language. So, as you know about that, dumb people and all, they are having the same language. So, in the similar manner as I was talking about GDMT, so even the kind of language that what we have for those kind of people, so it has got an advancement actually. So with respect to IT and with respect to AI and machine learning, so they are bringing it actually.
But they can replace that part in throat. So later then they can able to speak or not. Even if they can speak, how much percent it is efficient?
So you are talking about making the dumb to speak.
Yes, sir. Like they will
Okay.
implant that particular
That by
voice
using
box in the throat.
vibration, yes, 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 they have
Yes,
made
yes.
it actually. So by vibration, by getting that pulse and all, they're already made. So many products are there actually, but with respect to the accuracy concern, so it is under progress actually.
Okay. Thank you, sir.
Okay. In PMI, how to mention which operation? Okay. Pawan has asked on PMI which operation should be done part, not part. So it depends again. The operation will be entirely depend on the different type of application. As I was talking about that casting, whether it is a cast product or it may be a machine product or whether it is a digital product. So it depends. So based on that, we're gonna have different types of operation. As I said, we are having different platforms for product data management with respect to the different software that what we have, SolidWorks, Creo, and CATIA. Each and every software has their own PDM softwares. Innovia, for CATIA there is Innovia, and for Creo you are having Windchill, and for UG you are having a Team Center. Likewise, they are having different database to manage the product life cycle. So along with the modeling softwares and automation tools, so in future you will have to learn with respect to PDM softwares as well. So in which country there is a good scope for specialization and jobs in automation and robotics. So you are having so almost in all the abroad countries they are offering for automation and robotics actually. So in US you're gonna have a better opportunity for automation and robotics actually. So in India it needs a time. Okay, thank you. Any other further questions? Anil, is it Scrum Master or to send? Anil has further question. Is it a Scrum Master anywhere related to design engineers? Related to, so it is related to actually the agile manufacturing. That is again what it will be a different, as I said, the product data management software related to like that. So some what you mentioned. Scrum Master, yes. So it is what agile framework that what software and database that is happening that is related to what surveys, research, sales, marketing, and the recent technology that what we have related to that. We're gonna have what a platform. So how exactly the product life cycle will gonna happen? So the it's similar to the product data management softwares. But mainly for software software engineers. Canada is good for design engineers for opportunities. Okay, so we're going to have yes, a wide variety of opportunities are there in Canada, even for design engineers as well as being a researcher, faculty members. There are plenty of options you can have if you would like to go for Canada. So, what are datum shifts? Okay. In this term. Scrum Master. So I think Anil, I have answered for your Scrum Master question. Okay, can go. Okay.
I hope all the doubts are clear.
Okay. Any other further questions? Okay. Okay. Raghavendra has asked what are datum shifts. So datum shifts normally we're going to have from coordinate to coordinate. That is, for some features we're going to have coordinate what the thumb rule hands. What we call that as we're going to have some set of equations. That means the formulas we're going to write. So with respect to that, and for any deviations, we're going to have datum shifts. Anil, is it possible to shift career from design to CA domain? So you can have your change at any point of time, Anil. I think you have went through so many options. Sorry, is it a design engineer have stagnant growth when compared to CFD or CA? Then just keep one thing in your mind, Anil. So it doesn't mean what. It's not like that. Whether design engineer will want to sustain for a longer period of time, or he will become absolute, or CFD will become absolute, or CA will become absolute. It's not like that, because nothing will become absolute up to certain period of time. But still, that absolute will going to have a new innovation and new era will come, and it will be in the new form. So you just upgrade yourself with respect to that, and just do the same kind of what process in different manner. That's it. As we were not doing that CFD in earlier days, we were having only few kinds of software. But as the advancement has happened, you just keep updating yourself and just keep on adding the tools that what you are having, and what are all the other tools that you have to incorporate. As I mentioned, PDM tool, PLM tools, and then CAE tools. Each and every tools, you need not to have an in-depth knowledge of each and every tool. At least you can have one tool with respect to what design concern or analysis concern or programming concern. If you know the knowledge, then you can have what a better scope for further improvement. So at least if you know at least a base of different fields, so then you can suppose if you what get an opportunity in an industry itself to sustain your job, then there will be an option for company to what sustain you without any firing. So likewise, so it would be better if you keep upgrading with respect to the softwares. Next. Next. Any other questions? So Raghavendra, when do we use composite tolerance and when to use compounds? So it depends. As I said, when you are having multiple manufacturing process, when you are having casting and then machining product as like axles and the engine components. There we come across with the composite tolerance and component tolerance, and along with that stack analysis as well. So, so those are all the main fields where you can come across with the component tolerance as well as composite tolerance. Okay. I hope I have answered for all the questions that what you have posed. Any other further questions, either through chats or YouTube or by vocal? If you'd like to ask, please. Still, we have a time.
Thank you, sir. I hope all the questions are cleared. And participants, I have already posted the feedback link in the chat box. If you have any other further questions, you may add in the additional comments. There is a tab with the additional comments name, so you can add your questions there. We will share those to our resource person.
Okay, fine then. So thank you so much for giving a very good platform again, and thank you for Anil, Ravindra, and so many guys who have posed a very good question. Neil, I think you are doing so many research what are related to the information and the things that what is happening. Just keep upgrading yourself. You're gonna have a better future. Good luck and okay. Thank you all. Have a
Thank
good
you, sir.
evening.
Thank you for answering all the questions very patiently. Thank you so much.